Hey guys, so welcome to my our second unit on constellations. I like to start with this computer software that I have. So this is called Starry Night, and what you're looking at right now, this is actually the night sky tonight at 9:21. That's what time I'm doing this at, September 21st, and we're looking at the sky from here in Georgia. So right now we're looking to the north, and I'm using this as just an introduction to just show you the kinds of things that we're going to be doing for this unit. So when you're looking for the north, you should be able to see a bunch of constellations around here. I don't expect you to know these constellations yet, but you will eventually. This week, what my main concern that you need to learn is this up here. So if you look, it says gaze, and then you see this word, this symbol here. It says alt, and this says AZ. So that stands for altitude and azimuth. We're going to be talking about what that means today, altitude and azimuth. And then I can click here, and then we have RA and DEC. That stands for right ascension declination. And then down here you have LAT and LONG. That stands for latitude longitude. So we're going to be talking about right ascension declination, latitude longitude, and altitude and azimuth. Those are the big things we have to talk about this week going into next week. But I just like this program. It's kind of neat. Just shows you the night sky. I can click here and I can say show any of this stuff here. So I'm going to show you the constellations. And then the constellations pop up and you can see the outlines, star outlines of the constellations and the names of them. And then another thing I want you to notice with this program, look at the shape of the sky here. Think about, what's the shape of the sky? That's going to be important in a minute when we start my PowerPoint on this. But just notice the shape of the sky. I can go all the way up to the very tippy top, right, the point right above our heads. That's called our zenith, the point right above our heads. We're going to talk more about that. And then I can come back down here in the south and just go all the way around. So hopefully you're noticing the shape of the sky. And we're going to talk about the shape in just a minute. And then another thing we're going to need to know is this right here. So wherever the land and sky meet, think about what that's called as well. So here you have the sky, and here's the land, and right here where they meet, we need to know what that's called. So we're going to talk about that as well. And you can see all these constellations. So keep these things in mind as we're going through the PowerPoint. So guys, think about what you see when you go outside and look up at the night sky. Hopefully when you think about the night sky, you think about these things, stars, planets, the moon, clouds, airplanes, there's all sorts of things in the night sky, satellites, but those are all things we can see. And what we're going to do is we're going to try to learn how we can actually tell someone where these objects are located in the sky. And there's different ways to do that. I mentioned this earlier in class. I said we're going to be learning about the local, global, and geographic coordinate systems. Sorry, I said that wrong. Geographic, local, and global coordinate systems. That's what we're going to talk about. That it deals with latitude, longitude, altitude, azimuth, right ascension, declination. And then geographic deals with, what location, like where, proper names of things. And these are all things we're going to talk about as we go. So if you don't get all this today, that's fine. I'm going to spend a lot of time talking about each thing specifically. Today is more of just an overview of what we're going to be talking about during this unit. So when I showed you the PowerPoint, my software, computer software, I told you that I wanted you to look at the shape of the sky. So hopefully you're able to go outside and see the shape of the sky and notice that there's a certain shape to it. So when you look at it, hopefully you realize that it does not look like this. So does the sky appear to be like a box? This would just be kind of strange if there were actually corners in the sky. You'd see stars go across the sky and then they'd come straight down. And the sky doesn't work this way. The sky is not a box. And so hopefully you can realize the shape of the sky. And there's a reason the shape of the sky is not a box like this. So hopefully you realize that the shape of the sky is actually it's a dome shape. It's a half dome. It's a dome. Half sphere, which is a dome shape, sorry. So it's more of a smooth bowl. So you can always see stars. They're always going to rise in the east, and they're always going to set in the west. Always, always, always. They always rise in the east and set in the west. And then you're just kind of here in the dome looking up at them. And that hopefully you can see that when you go outside and look at the sky, that you can see it's a dome shape. The reason it's dome shape is because think about the Earth's shape. So the Earth it's not quite a sphere. It's actually called oblate. The Earth is oblate. It's not a perfect sphere. It's fat in the center because of the Earth's rotation, and that causes it to be a little fat. The rotation, because we're rotating about 1,000 miles per hour, and that causes at the equator the Earth to be a little fatter than a perfect sphere. But the reason we have a dome-shaped sky is because the Earth is almost spherical. But again, it's called oblate. If the Earth were more of a box shape, then we'd probably have a box-shaped sky, and that'd be kind of weird. But this is what the sky looks like. So that's the first thing I want you to notice, is that the sky is dome-shaped or smooth bowl-shaped. Now, you heard about this term in our last unit when we talked about the history of astronomy, and that was the term the celestial sphere. So a celestial sphere is a giant sphere, and inside of that sphere, the Earth is in the very center. Now, obviously, this is not drawn to scale because the Earth is not this big compared to the rest of the universe. So every star, every single star there is that we know about could be found on this sphere right here. This is the celestial sphere. So they are fixed points on this sphere, and then the Earth is in the center. And then we're, of course, on the Earth. And then you look here, you can see this line going straight through the center of the celestial sphere. We're going to talk about all this stuff later on. Again, this is just a brief overview, but this would be called the celestial equator, and it kind of runs right above this line running straight through the middle of the Earth. What would that line be called that runs straight through the middle of the Earth? That's called the equator. So you have the celestial equator, and then you have the equator on the Earth, and the celestial sphere here with the Earth in the center. So everything else, everything in the sky appears to be the same distance away from the Earth on the celestial sphere. And we'll talk a lot about this later on sometime. So objects on the celestial sphere are actually much larger than the Earth, but for scale-wise, we can't draw everything that way because there's just not enough room on the celestial sphere. So please don't think that the Earth is the biggest object, and we already know the Earth is not the center of the universe, but in a celestial sphere, we just put it there. And we'll talk more about the celestial sphere after we come back from fall break. So again, today I'm just giving you a brief overview of things we're going to be talking about during this unit. So we only draw the Earth big so we can see it more easily. That's the only reason the Earth is big, and every other object is usually much larger than the Earth. So I said this already, but everything in the sky can be plotted on the celestial sphere. Every object is plotted on the celestial sphere. All the stars, everything. The only thing that's not is our sun. So our sun actually goes, and I'll show you an example of a celestial sphere next week, but the sun is actually not plotted on the celestial sphere, and I'll show you why later on. But it deals with the path the sun takes across the sky, which is called the ecliptic. But all the other objects are plotted on the celestial sphere. And something else to keep in mind as well, if you're standing on the Earth right here, you cannot see all the objects on the celestial sphere. So if you're in the northern hemisphere, the northern celestial hemisphere, up here, you're not going to be able to see the stars that are down here. Why can you not see the stars that are down here? Well, the Earth is actually in the way, so you're not going to be able to see them. So you're only going to be able to see the stars up in the northern hemisphere, and then part of the stars in the south as it's moving. So we'll do some examples of that later on as well. So what I want to spend most of my time talking about today is how to describe where objects are located. So for this example, we're going to look at where objects are located on the Earth. So let's do a little activity here. So think about where you were born. What city were you born in? Now let's think about, you're going on vacation. I know we can't travel, abroad to Australia, anything right now with everything going on, but, maybe next year sometime after all this COVID thing is over, and you get to go on a trip finally. Maybe you're going to go to the beach in Australia. So you go to the beach in Australia and you see someone that you want to go and talk to, and you start talking to them, and they ask you, "Where are you from?" How would you answer that question? If they live in Australia, how would you answer where you are from? You know, think about what you'd say. Would you say, I live, would you say, I live off Hembry Road? Is that something you would say to someone that lives in Australia? Probably not, because they don't know where Hembry Road is. So the most logical answer would be, you'd probably say, "Oh, I live in the United States." And they might say, "Oh, well, where in the United States?" And you'd say, where do you think you'd say next? You'd probably say, "Well, I live in Georgia. Do you know where Georgia is?" And they might say yes. And then you'd say, "Okay, well, I live near Atlanta," because most people, if they know where Georgia is, they know Atlanta as well. You might even say, "I live in Marietta or Roswell." But when you're dealing with someone that is not familiar with your area, you're going to be more broad of an answer. So you're going to start by saying something like, "I live in the United States. I live in Georgia. I live near Atlanta." So that's going to be different. If That's going to be a different answer than if you are trying to study for a test with someone in your class, and you just met them recently and they don't know where you live, but you're going to get together and study. How would you tell that person where you live? Would you say, "Oh, I live near Atlanta, Georgia," or "I live in the United States"? Obviously not. They're going to be more of a local. They're going to know more about the local scene. So you could actually say what street you live on. You could say, "Oh, I live in this neighborhood. This is my actual address. This is where I live." That's because they're more familiar with the area. So that's just an idea of how you describe different locations to people depending on where you're at and where those other people are from. There's different ways of describing locations for on Earth, and there's also different ways of describing locations in the sky. Those ways of describing the locations of these objects are here. They're called the geographic system, the local coordinate system, and the global coordinate system. So for geographic, I just gave you an example. If you're talking to someone in Australia, you'd say, "Oh, I live in the United States. I live in North America. I live near Atlanta in Georgia." That's a geographic. When you get a little bit more specific, you deal with either a local coordinate system or a global coordinate system. So for us, we would deal with local coordinate system. If you're describing to one of your friends that you're going to study with, you would use the local coordinate system. "Oh, I live, 1 mile down Hembry Road," or "I live 1 mile to the east," or 2 miles to the west. That's a local coordinate system. Back when I was in school, we used to say there wasn't that much around, so we'd always use the big chicken for a reference. I'd say, "Well, you know where the big chicken is? Well, take a left over near the big chicken, and it's over there." That's an example of a local coordinate system because people familiar with the area are familiar with the big chicken. For a global coordinate system, that would be your latitude and your longitude. So this is what we use for science. So it's a very specific way of telling someone exactly where you're at, and we measure latitude and longitude with degrees. So example for global coordinate system, you would say, like, if we live near Atlanta, Georgia, right, or Roswell, or wherever, we would say we live at 34 degrees, excuse me, 34 degrees north, 34 degrees north latitude, 84 degrees west longitude. That's our latitude and longitude for here in Georgia, near Atlanta. 34 degrees north latitude, 84 degrees west longitude. So those are the three types of systems for locating objects on the Earth. We're probably going to do some examples with this later on, maybe on Friday for an activity. But we also use these three methods for locating things in the sky as well. So just as we can use geographic, local coordinate systems, and global coordinate systems to find things on the Earth, we can also use these to find things in the sky. So what do you think you would say if you're going to use the geographic system for locating something in the sky? You're not going to use a state or a city name or a continent or a country. What would you say instead? Well, hopefully you'd say, the name of a constellation or the name of a star. So you could say, "Hey, look over there near Polaris," or "Look at the northern star. look at Ursa Major. That would be a geographic system for finding things in the sky. For a local coordinate system in the sky, I'm going to go ahead and flip the page here because we haven't talked about this, and you're probably not familiar with these. So I'm going to talk about these. So geographic, for finding objects in the sky, you'd say the name of a star, the name of a constellation. For a local coordinate system, now remember, for local, that means for people in your area. So right around where we live in East Cobb, you could say the altitude or azimuth of something because we're in the same position on the Earth to see that object in the sky. So the altitude and azimuth are going to be very similar. So altitude is measured in degrees, and azimuth is also measured in degrees, similar to how latitude and longitude were measured in degrees. So altitude is the angular distance above the horizon to wherever the object is in the sky. And then azimuth, we're going to talk about this definition later on. It's kind of a wordy definition, but it's the angular distance from the north going eastward around the horizon to where the object is in the sky. So that might not make much sense right now, but hopefully it will later on this week and into the week after fall break. The other type of system, global coordinate system, that deals with right ascension and declination. So we're going to talk a lot about these as well. The main thing I want to tell you right now about the local coordinate system and global coordinate system for finding objects in the sky right now, you need to know that altitude and azimuth, the positions of, like, say, a star, for instance, using altitude and azimuth will change. Altitude and azimuth will change because it's based upon your position on the Earth. The global coordinate system, the right ascension declination, that will not change. The right ascension declination for a certain star is always going to be the same because it deals with global. It deals with the entire Earth, where we are all on the Earth. So it's a fixed position, very similar to latitude and longitude for on the Earth. So we mentioned latitude and longitude on the Earth. We said where we live at 84 degrees north and 34 degrees, I'm sorry, I said that wrong. 34 degrees north, 84 degrees west. So our position where we live will always stay the same. That's what happens with a global coordinate system. Same thing with right ascension and declination. So we'll talk more about right ascension and declination again when we come back from the break. Today, again, just an overview of what these words are and what we're going to be learning about. Okay, so we just mentioned this a minute ago. We talked about what a celestial sphere is. So the sky is a sphere with the Earth at the center. That's the celestial sphere. And then we just need to know a couple other definitions. Observers can only see the sky above the horizon. We mentioned that when I showed you an image of the celestial sphere. So the horizon, we said, we need to know what this definition is. This will definitely be in your test. We said where the land and sky meet, that is the horizon. So think about when you go to, like, the beach and you look out over the horizon of the ocean, you've got a very large horizon because there's no trees or anything in your way. All you're doing is seeing the ocean keep going for miles and miles and miles. Now imagine if you live in, like, the middle of a forest. You walk outside of your little cabin and you look up, you're going to have a very small horizon maybe because you might have a bunch of trees around you. So it just depends on where you're at as to what your horizon is. So a horizon, I don't like this definition. Please don't remember this one. All you need to know is where the land and sky meet. That is where the horizon is. So we're going to talk about an astronomical horizon, which deals with an imaginary plane tangent to the Earth at the observer. We'll deal more with this when we start talking about how to use altitude and azimuth for measuring positions in the sky. So we're going to do an activity with this later on sometime. Okay, so measuring positions on the Earth, we got to talk about that before we actually get going and doing stuff with altitude and azimuth. So we always use latitude and longitude for the global positioning system for figuring out where things are on the Earth. So we need to know these two definitions. You'll have these two definitions on your test as well. So latitude is the angular distance north or south of the equator. So the equator is that imaginary line that runs around the center of the Earth. And we know latitude is measured in degrees. So at the equator, you're at 0 degrees. Now think about how high latitude can go before it starts coming back down. Where is the highest latitude going to be on the Earth? Hopefully you realize that on the very tippy top of the Earth, at the North Pole, that's where you're going to have the highest latitude because it's on the very top. So that latitude would be 90 degrees north. And then if you go the opposite way, the lowest you can go on the Earth would be 90 degrees south. After you go up to 90 degrees, if you keep going, you're going to start coming back down towards the equator. Now for longitude, longitude runs around the Earth, and it's the angular distance east or west of Greenwich, England. Now I always get the question as to, why Greenwich, England? Why there? So there's a line that runs along through Greenwich, England, and that's called the 0 point line, or we call it the prime meridian. So the prime meridian runs through Greenwich, England. You're going to need to know that for your test. The reason it runs through Greenwich, England is because this system was developed there. This is where that started. So we have angular distance east or west of Greenwich, England deals with longitude, and angular distance north or south of the equator deals with latitude, both measured in degrees. Now think about how high longitude can go before it starts coming back down. So if we're running around the Earth, well, how many degrees does it take to go around the Earth, keeping in mind that the Earth is a spherical object? It's oblate. It's a little fat in the center, but it's round. It's a round object. So how many degrees are there in a circle? So if you go halfway around a circle, you're at how many degrees? Hopefully you realize that that's 180 degrees. So you go 180 degrees east, and you can go 180 degrees west. So that adds up to 360 degrees. So longitude cannot be any higher than 180 degrees. Latitude cannot be any higher than 90 degrees. So here are the two types of lines. So please don't mess up these lines. You need to know which line is which. So if we are running from north to south like this, going up and down, these blue lines here, and notice we're going around the Earth this way. Now, the Earth here is not round. It's cut in half. It's cut and it's placed down on like a flat paper. So if you keep going like this, you'd be going around the Earth, but it's not connected. So what kind of lines are these that are running north and south? These lines that run north to south but are going east and west are called which lines are they? Are they latitude or are they longitude? These blue lines, these are called your longitude lines, which means these pink lines are running east and west, but they're getting higher and lower going north and south. These lines are called latitude lines. So you have these lines, these blue lines are longitude lines. These pink lines are called latitude lines. The way I always remember it, I think of latitude. Latitude is fatitude. So a person's the fattest at the center. So, equator, fat part of the Earth, that's a latitude line. That's how I remember it. Latitude is fatitude. So latitude lines run across here. Longitude lines run up and down this way. So latitude lines that run parallel to the equator. Longitude lines that run from pole to pole, North Pole to South Pole, and it runs through Greenwich, England. The line that runs straight through Greenwich, England is the starting point, and that's called the prime meridian. Got to know these things. Got to know what latitude is. You got to know what longitude is. You got to know what the prime meridian is. You also have to know what the equator is. And you got to know that the prime meridian runs through Greenwich, England. It's not called Greenwich, it's Greenwich. So whenever we're face to face, I usually do an activity that deals with finding objects on the Earth, finding locations. I'm going to try to figure out an activity to do for you guys since we're virtual. But I'm going to go ahead and tell you, whenever you're dealing with latitude and longitude, these are the rules. So they're both measured in degrees, which is the unit that you're measuring latitude and longitude with. Latitude cannot be any more than 90 degrees. Longitude cannot be any more than 180 degrees. We've established that. When you're saying latitude and longitude together, you're always going to say latitude before longitude. You always say like northwest or southeast. You don't say west north or or west south. You don't do that. It's always northwest or southeast or northeast or southwest. Always say latitude first and then longitude. And then, whenever you're talking only about latitude or longitude, you're always going to include the word for which one you're talking about. So, for instance, I said earlier that we live at 34 degrees north, so you would have to say 34 degrees north latitude. The example I have here, 44 degrees north latitude. For longitude, you'd say 132 degrees west longitude, or for where we live in Atlanta, we'd say 84 degrees west longitude. So when talking about only latitude or longitude, make sure you include the words latitude or longitude for whichever one you're talking about. So keep that in mind when you're doing some examples with latitude and longitude. So quick review here. What are these blue lines called? Hopefully you remember that those are called longitude lines. And then these pink lines would be latitude lines. And again, the way I remember it, latitude is fatitude. So going across the equator, going across the middle, that's the fattest part of the Earth. That's the fat part, so it's latitude. Okay, last thing we're going to talk about today. So we just finished talking about the geographic coordinate system, the global coordinate system for finding locations on the Earth. Now we're going to talk about the local coordinate system for finding objects in the sky. So we do that by using altitude and azimuth. Here are the definitions. So these are both measured in degrees, just like latitude and longitude were. So I'm going to start with altitude because that's the easier definition. So think about like airplanes. Airplanes, when they're flying in the sky, they fly with altitude. They're flying at 30,000 feet. That's their altitude. That's the height they are above the surface of the Earth. So altitude deals with height, or in this case, an angular distance. So altitude is the angular distance from the horizon, and we already said what a horizon is. It's where the land and sky meet. So the angular distance from the horizon above or below the horizon. Above or below the horizon. That's the altitude. Azimuth, it's a kind of a wordy definition here, but hopefully it'll start making sense again as we go and do some examples with this. So azimuth is the angular distance from the north measured eastward to wherever the object is in the sky. Angular distance from the north measured eastward. That's called azimuth, and they're both measured in degrees. So going back to this object, we said this is a celestial sphere. We know that in the center of the celestial sphere we have the Earth. This would be you on the Earth. Now, there's one new word here that we haven't talked about yet, and that's called a zenith. So the zenith is the point directly above you. That's called your zenith. There's also another word, it's not on here, but I'm going to go and mention it. The point directly below you is called your nadir, N-A-D-I-R. So the point directly above you is called your zenith. The point directly below you is called your nadir, N-A-D-I-R. These are terms that just deal with your locations. And so you could say, well, if someone's asking you, where are you? You could say, oh, well, Polaris is at my zenith. Well, Polaris is at your zenith. I know exactly where you are because Polaris is the North Star. And if it's right above your head, where would you be located? Hopefully you'll realize that means you're located at the North Pole. The North Star would be right above your head. That's your zenith. There you go. That means you're at the North Pole. So those are two definitions we need to know. The zenith, what a zenith is, and then what a nadir is. So let's do an example here with just showing what altitude and azimuth are. So if you are here on the Earth and there's an object in the sky, you can actually measure from the horizon up to where the object is in the sky, and that angle is called your altitude angle, measured in degrees. And I'm going to teach you how you can actually measure altitude using your hands. You can actually use your hand as measurement tools to measure altitude and azimuth. So for azimuth, There's the object in the sky right there. But we said azimuth is a measurement of where the object is, but you always start with what direction? You always start from the north. So we'd start from the north over here. That would be the starting point to the angle. So like for altitude angle, we're starting here, right here, and then we're going up to the object. For azimuth, we'd actually start in the north, and then we're going to go eastward all the way around to wherever the object is in the sky. And that angle that's made, starting from the north and going eastward to wherever the object is in the sky, that angle would be called your azimuth angle. So this is your azimuth angle. Start from the north, go eastward to wherever the object is in the sky. The reason you always go eastward is because we have to have a standard of measurement. It would be confusing if you would just start from the north, but then you could go west or east. So we always start from the north and go eastward. And the reason we go eastward is because that deals with the next thing we're going to talk about with positioning systems, not today, but eventually we're going to get into what right ascension is. And right ascension deals with going eastward as well. So we'll talk about why that is when we get to that lecture later on, sometime after fall break. But for now, we just need to know from the north, going eastward is called your azimuth angle. And notice it doesn't go up in the sky, it goes around the horizon. We already know the angle that goes up or down is called altitude. The angular measurement going around the horizon, eastward, azimuth. Okay, so last thing we need to know for this lecture today, I just told you altitude, what altitude is, but I want you to know about the North Star. So the North Star, it's called the North Star because it's in a fixed position in the north, and that's Polaris. So common misconception with Polaris, many students think Polaris is the brightest star in the sky. It is not. It is nowhere near the brightest star in the sky. But it is fixed, which means it's above the Earth's axis, which means as the Earth rotates, Polaris doesn't really move. It stays right there in the sky. And you can see all the other stars and constellations moving around Polaris. But that's kind of important. You can use that for navigation. So what that means is since Polaris doesn't move, Polaris will actually change positions in the sky based upon your latitude. So the way you can use Polaris for locations, for traveling, things like that, you need to know about its latitude. So we just said, you know, the North Star, if you're at the North Pole, the North Star's location in the sky would be at 90 degrees. That would be the altitude for the North Star, Polaris. So where's Polaris going to be if you are in Atlanta? Well, look here. It says the angle of Polaris above the horizon is the same as your latitude in degrees. So that's how you can use it for navigation. So Polaris in the sky is going to be at 34 degrees north in the sky, right here in Atlanta. So you can always tell where Polaris is because you can actually measure up 34 degrees from the horizon and you'll see Polaris right there in the sky. Now, where is Polaris going to be if you're at the equator? At the equator, Polaris is going to be right at your horizon, right there at 0 degrees latitude. Does that make sense? So at the equator, it's going to be at 0 degrees latitude, which means you probably won't see it because it's going to be at the horizon. Here in Georgia, it's going to be in Atlanta, it's going to be at 34 degrees north latitude. Up at the North Pole, it's going to be at 90 degrees north latitude. What happens if you're at the South Pole? Are you going to be able to see Polaris, the North Star at the South Pole? Well, obviously not, because the Earth is going to be in your way. Where would Polaris be if you're at the South Pole? What's that word that we said? What's that definition? At the South Pole, if you're standing on the South Pole, Polaris is going to be at your nadir. It's the point directly below you. So hopefully that starts to make sense, these definitions. And the more we talk about them, the more we say them, hopefully that will start clicking and kicking in. But the angle of Polaris above the horizon is going to be the same as your latitude. So if you're ever lost in the woods and somewhere you need to figure out a way, which way to go, you could use Polaris for navigation actually. So you could see where Polaris is in the sky, and that can tell you what your latitude is. It's kind of a neat little trick.